So in sample problems 3, 4, 5, and 6, we kind of ran through some typical applications of the ideal gas law, looking at changing variable and unknown variable problems. What we're moving on to now is kind of thinking about manipulations of the ideal gas law, thinking about how we can apply density and molar mass to the ideal gas law. So the first thing I want to do here, and we had kind of gone through this derivation in class, so I want to review it here, is thinking about how we can manipulate PV equals nRT to incorporate aspects of molar mass and density. So if we take the equation that is the kind of the gold standard, it's all about PV equals nRT for this chapter. If we take this equation, what I want to do is have us think about quantity in a different way, right? Normally quantity we think about as moles. But moles is really mass in grams divided by the molar mass, which is units of grams per mole. So unit-wise, grams would cancel here, 1 over moles would equal moles. So we can get to moles by taking the mass and dividing by the molar mass. Well, what that allows us to do is I'm going to put this piece of information into this equation, okay? So I'm going to kind of combine these two, and so PV equals M over, so I just essentially took what we said this was equal to and put it here, and I substituted in. Okay. Keep in mind, anytime you see a lowercase m, that refers to quantity and it refers to it in grams. We're going to see that over a few chapters here. I'm going to kind of manipulate this equation a little bit more and see if this makes sense. Algebraically, I'm going to move my molecular weight over here. I'm going to move my volume over to the other side. So all I've really done is just manipulate PV equals nRT. So what this allows us to do is have an equation now that relates quantities in terms of molar mass. Mass over volume is density. So it takes kind of the quantity and volume parts out and allows us to think about density and molar mass. And so, again, this is going to be important. We'll work through some problems, but what it allows us to think about is if we know, for example, the pressure and the identity of a gas, because we know the molar mass of it, if we know who it is, we can then, knowing the temperature that that gas is, think about the density, or kind of use this in a whole bunch of different ways to solve for different unknowns. So, again, that's what this first problem is about. So, to apply a green chemistry approach, a chemical engineer uses waste carbon dioxide from a manufacturing process instead of chlorofluorocarbons as a blowing agent in the production of polystyrene. And just as a little kind of neat side note here, when we think about what's really going on here, when you make styrofoam, you take a polymer and you blow air into it, and that's how you make it foamy, and then it cools, it solidifies, and you get polystyrene, you get styrofoam. Well, chlorofluorocarbons are really bad for the environment. So if you use carbon dioxide to blow it up, you're not using something that's bad for the environment. And even better, you're actually using waste carbon dioxide that's produced in a manufacturing process. And rather than that carbon dioxide going out into the environment and causing greenhouse gas effects, you're actually using it to produce styrofoam here. So again, little aside there, that first sentence really has nothing to do with the nuts and bolts of the problem. The nuts and bolts really come in this second part here. So like I do with all my problems, I like to write down information I know and think about where I want to go with that information. Well, they tell us that we want to find the density in grams per liter of carbon dioxide. So that's a piece of information that we want to go. That's an answer. So find the density of it, and they tell us they want units of grams per liter, and they tell us that we have carbon dioxide gas, and they also tell us that we want to know the number of molecules, so the number of molecules of carbon dioxide per liter. So they tell us at standard temperature and pressure, so we know that the temperature is going to be equal to 0 degrees Celsius, the pressure is equal to 1 atmosphere. We know that the identity of the gas is CO2, and the question is, can we get to density and then the number of molecules of carbon dioxide per liter? Well, looking at this equation here, right, they gave us pressure. Because we know who the gas is, we have the molecular weight. We want to find the density. Mass is always going to be in grams per liter. And they tell us the temperature. So they actually give us information that we need here. So again, using this equation that we just figured out, pressure times the molecular weight is equal to the density times RT. Again, they give us the pressure. They give us that in atmospheres. Temperature, as long as we convert that to Kelvin by adding 273, we get to 273 Kelvin. So they give us that. R is our good old gas constant that we know that. We know that the molar mass of carbon dioxide is equal to 44.02 grams per mole. So again, the only reason we know the molar mass is because we know the identity of the gas. And now we can solve for our unknown here, which is our density. And m over v, m is going to have units of grams, v is going to have units of liters, so that gets us to the first part of the problem that we want. Now the question is how do we go from here to here? Well, hopefully everybody sees that we can go from grams to moles using the molar mass. And we can go from moles to molecules using Avogadro's number. So a little bit of time here to set up our roadmap, but once we have our roadmap set up, it's pretty easy to execute. So I'm going to go ahead and I'm going to solve this problem for the variable that we want. Our density, m over v, is going to be equal to the pressure times the molar mass times R times T. Putting our pieces of information in here, we have 1 atmosphere, 44.01 grams per mole. Sorry, I had the wrong, I was going by memory here and that was not right, 44.01 grams per mole. R is again our 0.08206 liter atmosphere per mole Kelvin. And our temperature is 273 Kelvin. Go ahead and solve this for m over v, and you get 1.96 grams of CO2 per liter. So that is part 1. That's our density. Now we need to complete the rest of our walk here to get our answer in units of molecules per liter. So 1.96 grams of CO2 per liter. Use the molecular weight here. 44.01 grams of CO2 is 1 mole. 1 mole of CO2 is 6.022 times 10 to the 23rd. Molecules of CO2, and that equals to 3 significant figures, 2.68 times 10 to the 22nd molecules of CO2 per liter. Okay, now I kind of ran out of room here at the bottom, but this problem asks us, there's an A part and a B part. The A part is at standard temperature and pressure. The B part says at room temperature. So I'm going to just grab another piece of paper here. And if we go ahead and we solve the B part, I'm not going to need a lot of room here. For the B part, the only part that is different is that we've got our T equal to 25 degrees C. So that means our T is going to now be 293 K. So what that really means is we carry out the same calculation. So I'm not going to run through it, but all that changes is this piece of information right here. Same calculation means we get 1.83 grams per liter, and the same conversion to molecules is 2.50 times 10 to the 22nd molecules per liter. This should have followed our predictions, right? If we handle a prediction here, we predict that if you increase the temperature, will decrease the density of the gas, right? We talked about that with our hot air balloon. So that's the principle behind why a hot air balloon rises. Okay, so again, B part of the problem, pretty straightforward. Same calculation. All that's going to change is that this 273 will now be 293 293. Oops, excuse me, this was 20 degrees. That's why it was 293. So 20 degrees C.